Hi guys, long time no see. So, so today we're gonna study about something much different. Let me write it down again here. Some clearly, I like the when the handwriting is clear. So, so today we'll talk about why the flow of blood should be laminar. Okay, why the flow of blood should be laminar. That's the thing we're gonna talk about. So at first, we'll study about fluid dynamics. So we're going to study about fluid dynamics or fluid dynamics or characteristics, whatever you can say. Sometimes I get confused about should I tell it mechanics or the dynamics. Yeah, because we are talking about how it moves, right? So we should talk about the mechanics. We should talk about the dynamics, but when you include mechanics, we should include the force part, I guess. Bernoulli's law and upthrust, those whatever. Okay, no matter. That's not our main problem here. So what is laminar flow? Suppose this is a pipe, okay? This is a pipe. This is a pipe, and we're gonna use blue color for the water flow here. So, okay, when the flow is laminar, it flows like this. I mean, it's laminar, okay? Maybe I can say like this here, okay? Like, this is how it flows. Or maybe I should do something else. Wait. For example, the fluid flow here. This is water moving at a velocity here. Moving at a velocity. Here, when the fluid is going, for example, this is fluid 1, and this is fluid 2. They will go without disturbing each other. They'll flow laminarly. They won't disturb each other or something. Like you see fluid flows transforms from laminar to turbulent when the velocity increases. There's a thing called critical velocity. Critical velocity is a term when when the when the fluid flow has two regimes, laminar and turbulent. So when the critical velocity is reached, in that velocity, laminar flow starts to turn in turbulent flow. It's kind of like static friction, okay? When the force is equal to the static friction force, the object starts moving. It's kind of like that. You can think of that terminology. That's how it goes, okay? So and let's now talk about turbulent flow. So when the turbulent flow happens, that's how it goes here. Like it's like when you see in a steam engine or something or nuclear factories, gas is coming out like this, like this. You see these type of flows, okay? These type of flows are turbulent. And when this happens, lots of fluctuations, and there's a term called eddies. There's a term called eddies. These eddies are like that. If you watch Ninja Hattori cartoon, you will think about it like that. Ninja Hattori has a logo in her cheeks, you know. I wasn't once a very much cartoon fan, like so lots of eddies are generated here. That's a turbulent flow here. That's a normal stuff. Okay. Now let's talk something graphical. I want to add another page here. Where should I add? So now let's talk about graphical here. There's a velocity with respect to time. Now we're going to talk about laminar flow. It's straight as hell. Okay, this one is laminar. But when you talk about turbulent, so here the velocity the velocity of the fluid here with respect to time is the time averaged of the velocity. It's a straight line, you know. Now for the turbulent flow, what you can see, it kind of happens like this. It kind of happens like this. And then we're going to draw a dot dot line here. This is a straight line, by the way. So it's like think of it a line, and it should be straight, but lots of fluctuations are happening here. Okay. These fluctuations happen around this turbulent flow. Okay. In a turbulent flow, you need to add the time average velocity with the fluctuation component as well. Fluctuating component as well. I'm not. This term might be wrong. If there's something wrong, I will tell it out to you later. But that's how it happens. Okay. So basically what I say, that when the flow of a fluid reaches a what did I say? Reaches a critical velocity, the flow starts to turn from laminar to turbulent. But there's another catch here. We will learn a unique concept today: Reynolds number. You see, whenever I study about Reynolds number, what reminds me about is Ryan Reynolds. So whenever you forget about Reynolds number, think about Ryan Reynolds. You just smooth like a fluid, you know. I love her. I love him. Sorry, whatever. So here, what's the Reynolds number here? This density, characteristic length, and the dynamic viscosity. This is the equation of Reynolds number. Now here's another catch here. You see, this term is related to the inertial force. And this term is, is about the viscous force or the viscosity, whatever we can think about. When this increases, the fluid becomes turbulent. But when this increases, the fluid becomes laminar. You see, in laminar flow, it's more about how the object is moving, you know. You guys might have studied about resistor force in the fluid. If you did, if you did study about it, like C1 R V and C2 R squared V squared. This thing, okay? You see, this is the viscous term. And this is the pressure term. And now you might ask, why it's a pressure term? Think of it, it's like that. The pressure is proportional to force by area. Pressure is equal to force by area. The pressure is inversely proportional to the area. And if we think, suppose a beer or a cylinder, the area, the cross section, its cross-sectional area of a cylinder is pi r squared, you know? So the cross-sectional area of a cylinder is pi r squared. So that's why it's a pressure term. Anyway, this is out of topic. You might not know this, but I was just using it to teach it to you guys. Using this, we can also figure out the critical velocity using this, by the way, but we will not do it here. So the Reynolds number has a range. What is that range here? The Reynolds number has a range from 0 to 200. It's laminar. From 2000 to 4000 is called transitional, or less than 4000 transitional flow. We'll talk about it later. And here the flow becomes turbulent. Turbulent. Sorry, I shouldn't use this. Okay. Now you might. By the way, I didn't mention another thing here. In this equation, the rho is the density of the fluid, the velocity, and this is called the characteristic length. Now, what is the characteristic length here? You need to understand. Suppose I'm giving some fluid lines, okay? These are lines of fluid. Okay. Now, now imagine. Now imagine if we have a sphere. If we have a sphere here, what will be the characteristic length of the sphere? Can you guess it? Think for a moment. The characteristic length is about. What is the characteristic length, anyways? When the object is in a fluid and it's moving around, there should be a length of an object, like in reference frame, not the exact. So here, I'm gonna tell you, pause for 5 to 10 seconds and think, well, what could it be? So the characteristic length here is it's the diameter of the sphere. Sorry for my stuttering, by the way. I have an issue, you know. I rarely speak that much. Problem of mine. I don't know what it is. Okay, this is called the diameter of the object or sphere. And for the same goes for the pipe here. For the pipe, this is what happens. But that's how it goes. Okay, that's what's the cat. And for you guys, whenever you guys study aerodynamics, you might see something shaped like this. Yeah. For this, the characteristic length is the arc. It's the length of the chord. Sorry, chord. Okay, this should be the characteristic length here. Anyways, that's not the important thing here. I'm just telling you to know what thing actually means here. So let's set another page here. So now let's come to the important topic. This is a human body. I'm gonna do like, and we have a teeny weeny heart here. Okay, teeny weeny heart, and it pumps blood from everywhere. Pumps. Maybe I don't know. Do you guys even know or not? When somebody has a block on his heart, you'll see in the calves of a muscle. Okay, in the calves of a muscle. Yeah, you see the calves here. See, the calves has a heart shape. So when somebody has a block in his heart, or has it's going through a heart failure, maybe heart issues, you'll see this portion will shrink. The calf muscle will shrink here because when the heart cannot get enough blood or pump enough blood, then for surviving it, for keeping the blood flow continuative, they use the calf muscle here. They pump the blood from here, actually. I don't know the exact term, but that's what I'm trying to say here. So let's try to do something different. Okay. But there's a thing called why the flow should be laminar and not turbulent. Before that, we're gonna try to understand. Suppose this is a pipe. We're using lots of pipes here. And this sounds like. Just imagine the flow is laminar. What will happen? What will happen is, see this portion here, the entire this portion. Here, the velocity will be like this. Fluid velocity movement. This will be like this. Will be this. This is the maximum. Lowers, lowers, and then zero here. And now why this is zero, I'm gonna tell it to you later. As you can see, it's a parabola. It's a parabola here. It's a parabola. Now why it is in a laminar flow, the, the flow velocity is the maximum when it is at the center of the pipe. Like it's literally in the center point pipe. Like here, it has the maximum velocity. And here, the velocity is zero. Why? It's called the no-slip condition. It's called the no-slip condition. This thing is also very much important in aerodynamics, but I don't want to talk much about it here. I'm going to talk about the amount of knowledge I have and try to explain it to you. Here, okay, what you see, the flow is like the flow here is this, and it increases, and it's a maximum here and then decreases. But that's how the flow in laminar way works. Now, for turbulent. For turbulent, I'm gonna take it's kinda like this. It's kinda like this. Before I say something, this shape is about the time average velocity here. But if you want to know the world what's happening in real time, this is what's happening in real time. The fluctuating component. This is the thing what's happening here. You need to understand these stuff. So, now we come to our most important part. Now tell me, this is a heart here. This is a heart. I don't know how to draw hearts. Whatever. Okay, like this is a heart here. Whatever. When it is very much difficult, pull or push something. Suppose, like in a chimney, okay? Suppose you're using a process pull out water from here. Like pull out water from here, pull out water from everywhere. So you want to try to pull it. Okay? You want to try to pull it. But the fact is, in laminar flow, there's a thing there's a thing called pressure drop. Yeah, the pressure drop. Why the pressure drop is more important here? Because that's the main reason why it's very much difficult. It would be very much difficult if our blood flow was turbulent. The heart would have faced difficulty for pumping blood. Why? You see, when fluid moves in, suppose this is our blood tube here, and this is the incident pressure, and this is the outside pressure. But you see, the pressure drop here, the drop of pressure is drop of pressure here is larger in turbulent flow, and the pressure drop of laminar flow is less. So when the pressure drop is less, suppose think of it as something like a pipe. Okay, think of it like a pipe. Like you see, when you try to in a pipe, okay, in a water hose pipe, when you push water in here, like from a water hose or something, or from your basin or tube well, something, okay, when it goes through a pipe, you will see the water bit comes with less pressure. You see, the incident pressure which the water entered to the pipe in a turbulent flow, it comes out in a less pressure, right? In that case, if the pressure is less, the blood flow would be very much low for average human body to survive daily life. Because of that, our blood flow is laminar. And for that, because the pressure drop is low, we can easily pump the blood in our body. So I hope you understood here. Like that's the main difference here I'm trying to talk about. Okay. Sorry for the my teaching style, okay? I'm still new in here, but we'll try to explain stuff more broadly and clearly. Um, yeah, that's the thing here. So the summary is the pressure drop in a turbulent flow is greater comparing laminar flow. So that's why the heart, I'm gonna draw it like this here, will feel pumping blood from body. So that's it, guys. This is what I was trying to teach you about. I hope you guys liked it or something. And I came after a long time, 2 months break. I was confused about what to do, what not to do. And also, I have further new plans, for this channel. I've seen one thing, like in the YouTube channel for the A-level students, especially for the Cambridge one, there's very lack of resources for further math in YouTube. I was thinking, I'm planning to upload video about A-level further math topics because I want students to be helped so that they can improve their. I'm also a A-level student, by the way. I have my exams very soon, but as I told you, I want to teach you guys what I learned daily. No matter if it might be scrambled or messy, but still, I believe in the Feynman law. If you want to master something, you have to teach it to someone else, unless you won't master it. Yeah, that's what it is. Thank you, guys. Hopefully, you'll like this video, and if you want, you can subscribe or do whatever you like. Yeah, that's it. Yeah.